Welcome everyone. Download this handout at spatial.berkeyacademy.com, or I'll try to remember to put it in a link in the description to the video below. But download this PDF handout here because we're going to go through all the common kinds of models here. It's not going to be anything scary. This is a re-record of my old version of this video, and I'm going to bring some updated material here as well. So download this, print it out, sit back and relax. I'm also going to keep rambling for a while about some different software and give you some suggested readings to give you some background on some of this stuff. So print this out, grab your favorite beverage, and join me for a discussion about spatial econometric models. So what we're going to do here is start with the idea of ordinary least squares regression. And let's just suppose we were doing a fictitious study looking at the causes and things that are correlated that can help us predict the unemployment rate in various states in the United States. And so just to visualize this, let me bring up a map as always. If you're doing an OLS regression, ordinary least squares, it doesn't take space into account, except sometimes people would use a dummy variable for various regions of a country. So you might have a dummy variable for the Northeast, the Southeast, and the West, or something like that. But otherwise, there's absolutely no spatial recognition that when you're studying something like growth rates or unemployment rates or incomes, that nearby states probably impact each other in some way or another. Instead, we just spatially, without looking at any kind of spatial interactions, would say, okay, we have our dependent variable. Let's just suppose that's the unemployment rate. And that's some linear function of the y-intercept plus some slope times some explanatory variable, say education levels, and plus another slope times another explanatory variable. Say this is per capita income or social capital. We could add a lot of different variables in here. And then we have this stochastic error term here, something that we're not going to be able to explain even if we have all of the explanatory variables. There's some randomness involved to these outcomes. Now, this is one way that you might be more familiar with seeing these kind of linear models written. We're going to stick with the matrix vector style because it's a lot more compact notation. But this kind of notation here just says that y, a vector of all the unemployment rates in the various states, can be written as a function of the explanatory variable matrix, the observed values of those variables, times a vector, a list of all the slopes, beta 0, beta 1, beta 2, etc., plus a vector of all the different error terms of all the different states. So again, nothing spatial there. But when we get into spatial econometrics and spatial statistics, we want to look for explicit spatial relationships. So what we do is we measure who are neighbors with whom using what we call a spatial weights matrix W. And later on, we'll look at what these things look like. We'll talk about some of their properties. But for now, I just want to keep this light. I want to keep this a very big picture sort of thing. Just take it for granted that this spatial weights matrix W tells the model which regions are neighbors with which other regions. Now we can define neighbors in a lot of different ways, and again we'll talk about this a little bit later on, but let's just visualize here, for example, that if we had a particular state, let's say North Carolina, where I live, if we wanted to define neighbors, the way that makes most sense to me is just, well, you're a neighbor if you touch, right? So Virginia here touches, and Tennessee and Georgia and South Carolina all touch North Carolina. And so they'd be the neighbors. But there are other ways that people define neighbors, depending on the circumstances. Some people might say, well, I want to define neighbors as any state whose centroid is within, say, a 500-mile radius. We could make a big bubble, and all the states whose centroids are within that bubble, or states whose boundaries are anywhere within that bubble, we might call them our neighbors. Another way, instead of just saying you're a neighbor or you're not a neighbor, we might say, well, you're a stronger neighbor if you're closer, and you're less strong of a neighbor if you're further away. So we could do a distance-weighted neighbor relationship. A lot of ways we could do this. But however we decide, we ought to carefully think about what we're doing. And let's just suppose we've decided to use a simple contiguity matrix. If you touch a state, you're its neighbor. If you share a border or a corner. Sometimes we call this a queen sort of neighbor relationship based on a chessboard, the ways a queen can move on a chessboard. So how might neighbors affect a neighboring region? Well, there are three main ways that we could think about this happening. First way, A, the value of unemployment, Y, in a region might impact or somehow be related to the unemployment rate, Y, in a neighboring region. So if, for some reason, we think that if North Carolina has a high unemployment rate, that might somehow cause a higher unemployment rate or lower unemployment rate in neighboring states, we might think about this as being a lag Y, spatially lagged Y kind of model. Now, another way that we might see this kind of spatial relationship, instead of the unemployment rate in one region somehow directly or indirectly impacting the unemployment rate in another region, it might be that the values of the explanatory variables in one region might affect or be related to somehow the dependent variable in another region. Let's look at our map to see how this might work. So again, if we're explaining unemployment, we might think about the explanatory variables, things like income or racial composition or education levels or social capital. And we might suspect that if the income in a state like Virginia, to the north here, or the social capital levels, or something like that in Virginia, if they're higher, that might decrease the unemployment rate in Virginia, but it also might somehow impact the unemployment rate in North Carolina. If people have high incomes in neighboring states, that might cause them to spend more money in the neighboring state, therefore reducing the unemployment. So that might be a way that these effects spill over. So again, two different ways that we've talked about so far. Lag Y, so the unemployment rate in Virginia might impact the unemployment rate in a neighboring region, North Carolina. This might be if there are a lot of unemployed people in Virginia, perhaps they migrate to a nearby state looking for work, thereby increasing the unemployment rate in North Carolina. Just one idea. So that'd be a lag Y. A lag X would be the income, the education, the social capital in Virginia might affect the unemployment rate in North Carolina. Now, a third common way we might think about this spatial neighbor relationship working out is that the residuals in one state might be related to the residuals in another. Now, in time series, this would be what we would call serial correlation, that the values of the residuals are related over time. Here, what we're saying is that the residuals might be related through space. So we call this, instead of serial correlation, we call it spatial autocorrelation. What might this mean? Well, remember that the residuals are a component of the dependent variable, say unemployment, something about that unemployment that we can't explain, some unexplained variation in that. And it might be that in a region, say in the southeastern United States, that in these states they have similar kinds of industries, and we're not including those industries as an explanatory variable, however. So we might have a cluster of states all in the same area that all have higher than expected unemployment rates because we've omitted a variable. And so it's being picked up in the residual. So that might be an example of how the residuals are going to be spatially related. So we might have a cluster of unexpectedly high unemployment rates in one region, another cluster of unexpectedly, at least according to our model and according to the variables we're using, unexpectedly low unemployment rates in another. So 3 different ways, standard kind of ways we can build in spatial relationships into our models. Lag y, it's where the value of the dependent variables spills across regions. Lag x, this is where the values of the explanatory variables in one region help predict the values of the dependent variable in another region. And third, spatial autocorrelation, when the residuals might be related to each other across space. So how can we build these into a model? Well, if we build all 3 of these things into one large model, this is what we call the Manske model here. A Manske model says y, the unemployment rate, is going to be equal to rho, some multiplier, some fraction, generally less than 1, times the neighboring, so w, anytime you see w, read that as the neighboring values. So rho times the neighboring values of unemployment, that would be building in the first idea here, the lag y's. So rho wy. Other determinants of a state's unemployment rate would be its own characteristics, its own explanatory variables, the income, the education, the social capital. But also the neighboring. So here's the neighboring values of x, wx, theta, where theta is a vector of a lot of different slope parameters. So instead of calling them betas, like we would for our own characteristics, we're calling them thetas. So this would be, how does my neighbor's education affect my unemployment? How does my neighbor's social capital affect my unemployment? So that's what's going on here, plus u. So u is an unexplained term. But in the Manske model, u is a function of, so my unexplained variation is a function of my neighbor's unexplained variation plus some white noise term, totally random stochastic error term here. So this is called the Manske model. Now, so the Manske model is kind of the fullest version of a spatial econometric model that you could have. Here's the problem, though. It's been generally found that these models are, how would you say, under-identified. It's very difficult, if not impossible, to get estimates for all of these things simultaneously. First, there's going to be a lot of multicollinearity is just the word that comes to mind, that if your residuals are spatially correlated and the value of the dependent variables are spatially related and the value of the explanatory variables are all spatially related, it's going to be very difficult to get coherent and precise estimates of all those different factors with your data set. So instead of trying to estimate this Manske model, the most complicated model that people generally try to estimate is what's called the Collegian-Pruka model by Harry Collegian and Ingmar Pruka, who are, I think, still at the University of Maryland. So if we set this theta term equal, sorry, not theta term, but theta vector, basically what we're doing is we're assuming that all of these neighboring explanatory variables do not affect us. Then this Manske model becomes simplified to just this model. All we're doing is we're removing this one term and that's what we call the Collegian-Pruka model. So we're simplifying it down. And Collegian and Pruka have found that they can get solid estimates for these kinds of models. So this is one of the camps, one of the groups of people that advocate that this is the way to go. You should start here and estimate this model. A second camp, though, is Jim Lesage and Kelly Pace. And Lesage and Pace say instead of assuming that those neighboring explanatory variables don't matter, let's set this lambda equal to 0 right here. And when you do that, you get what's called the Spatial Durbin model. And the Spatial Durbin model is more clever than it looks just on its face. So the Spatial Durbin model says that our unemployment rate in a state is equal to some function of neighboring unemployment rates plus our own explanatory variables plus neighbors' explanatory variables. So that's what's called the Spatial Durbin model. And what's ingenious about the Spatial Durbin model is you can actually, if you start with the Spatial Durbin actually encompasses several different ways that you can reduce it down to other common models. First way, that's obvious. What if this row here equals 0? Well, if row equals 0, that means that neighboring values of unemployment don't affect our unemployment. So when you restrict that down, that just becomes what we call a spatially lagged X model, right here. And it just says, so the SLX model, as we call it for short, it just says that our unemployment rate is affected by our own explanatory variables and explanatory variables of neighboring regions. Now, another way that we can simplify this equation number 4, this Spatial Durbin kind of model down, is what if we set this vector of thetas, like we were talking about before, what if they were all equal to 0? Then we're either making the assumption, or we sometimes let the data tell us, is this true? We can test to see, are all of these slopes 0 for all of these explanatory variables for the neighboring values of these explanatory variables? If those are all 0, then all we're left with is the lag Y model, or the spatial lag Y. And so we're going to be left with our unemployment rate is equal to some function, some weighted average of neighbors' unemployment rates, plus something having to do with our own explanatory variables. So this is called a spatial lag model, although some people call it a spatial autoregressive model because of its similarity in some ways to a time series autoregressive model. But the really brilliant thing about the Spatial Durbin model, and this is the thing that Jim Lesage and Kelly Pace did with their book in 2009, is they pointed out that the Spatial Durbin model is really nice because it can also give you another model if you simplify it. And that is, what if you assume that the theta, instead of equaling 0, what if theta, again, remember this is a list of slopes, and this is a list of how do my neighbor's explanatory variables affect our dependent variable, our unemployment rate. If those slope coefficients happen to equal minus rho, again, what's rho? Well, rho is the strength to which neighboring values of unemployment affect our unemployment. So minus rho times beta, that's the vector of how our own explanatory variables affect our own unemployment rate. If that happens to be true, and we can test to see if this is true using the data, then equation 4 here, the spatial Durbin, will simplify into just a spatial error model. And why is that? Well, because basically what happens is if theta is exactly equal to minus rho beta, lambda is going to be the same thing as rho. How can you see that to be true? So note, this math is probably not technically correct. I am not a master of matrix algebra, and I'm not going to go through this course this way. There are lots of other resources for that. What I'm trying to do is give you the intuition as to how these things work. I'm not going to bore you with math, but this one, just few lines of we'll call it pseudo math, helps you see why this restriction works. It gives you the intuition here. So if we start with the idea that we're looking at the spatial Durbin model here, and we plug in this identity that rho equals minus lambda times beta, or sorry, theta equals minus rho beta. We're just plugging that in here for theta in the spatial Durbin model. And what do we get? Well, we get our unemployment rate equals our neighboring values of unemployment, right? Because y equals x beta plus epsilon. Just making that substitution there. Plus, okay, so this is our own variables. How do they affect our unemployment rate? Plus wx minus rho beta, just making that substitution for theta. And then if we distribute this, rho wx beta right here, plus rho we right there, same x beta carried down, plus wx minus rho b, what happens? Well, you see here we have two terms that are basically going to cancel. Right here and right here. And again, I'm not trying to do a formal mathematical proof here. I'm just trying to get you to see where this cancellation comes from. If we make this strange sounding assumption here that theta equals minus rho times our vector of betas, what you end up with when those cancel is just that y equals x beta plus our residuals, but we're allowing our residuals to equal a weighted average, or to be affected by a weighted average of our neighbor's residuals there. So that rho we comes in there. So just to recap there, Lesage and Pace argue, and I buy this. This seems to be the most logical way to me to proceed. If you don't know, sometimes you should know. Sometimes you should have a good idea as to what structural model your data should have if you think about it. But if you don't know and you're doing a specification search, how should you proceed? Well, just like with all areas of econometrics, if you ask 1,000 econometricians, you're going to get about 800 different answers about how should you proceed with a specification search. In spatial econometrics, it's the same way. There's no unanimous opinion, but I like Lesage and Pace's approach, which say, look, first, estimate the spatial Durbin model because it's tractable, number one. We know that we can estimate these things, and we can get pretty good estimates of these coefficients. And then you should test to see, would it make sense to restrict the spatial Durbin model? And you can test restrictions in three ways. You can see if a spatially lagged X is more appropriate. You can see if a spatial autoregressive model is more appropriate. Or you can see if the spatial error model is more appropriate. But starting from the spatial Durbin model. Now, if you estimate the spatial Durbin model and you're getting strong, statistically significant coefficients for all of these spatial parameters, fine. Maybe that's a good model to go with. But if not, you can test these restrictions to see if one of these simpler models could work. Even going down to the fact that, hey, maybe your model's not a spatial model at all, and maybe this lambda here is also 0, in which case ordinary least squares would be a fine model to estimate. Maybe there is no spatial dependence in your model at all. Now, another common way, so that's one of the big camps, is the Lesage and Pace camp, and that's where I put myself. But I also appreciate the other arguments that are out there. Let me just very quickly tell you about the other main camp. The other main camp is Luke Insulin and his group. And Luke Insulin basically says, look, I advocate that you start with an OLS model. Just estimate a non-spatial model, and then what he does is set up some Lagrange multiplier tests, which ask the question, should we expand the model? And he focuses mostly on expanding it to either the spatial lag model or the spatial error model. So Luke Insulin favors these two, the spatial error model or the spatial lag or spatial autoregressive model. But he takes a different approach. Start with OLS and see if you should expand it using some Lagrange multiplier tests. Lesage and Pace, they start with the Spatial Durbin and then do tests to see if you should make the model simpler. Now let me just mention a few other common extensions these days that people are working with these models. It's not just cross-sectional models that people are doing anymore. There are panel data models that people have been doing for several years, including some work on dynamic panel models. So when it comes to, say, cross-country growth regressions, some people are using these. There's a good paper here, Journal of Geographical Studies by Paul Elhorst, 2012, that gives a pretty good review of these. And I have a list of these articles on the next page on the handout here. Other examples are some people are setting up models with more than one spatial weights matrix. Just as an example, you might have one spatial weights matrix that might be truly spatial, where it's counties. You might have another spatial weights matrix which might tie those counties together in a different way than spatially, maybe tie them together based on some sort of heritage, where people in a region where their ancestors came from, for example. That might be a way to set up not really a spatial connection, but more of a deeper historical connection that might help explain the relationships between these neighbors. Lesage and Pace in 2011 in the Review of Regional Studies, they have an article. It's free and open source journal. And again, I have a link down here to that article called Pitfalls in Higher Order Model Extensions of Basic Spatial Regression Methodology, to give you some things to think about whenever you want to try to go with multiple weights matrices. Another area that Don Lacombe, buddy of mine, has been working on is spatial hierarchical models. Let me show you a visual of what that might look like here. Spatial hierarchical model says you have, say, 2 levels of geography that you're interested in. These smaller regions here are counties, and the larger regions are states. A spatial hierarchical model would say that within a state, there's a spatial relationship, that counties affect each other within the state. And this could be an error model, a lag model, or any of those that we were just talking about. But then there's another spatial relationship that between states. States impact each other. So neighboring counties within a state affect each other, and then the neighboring states have an impact on each other as well. This is very useful when you have different levels of measurement for data trying to explain the same thing. So for example, you might want to explain renewable fuel use in a state. What percentage of the electricity in a state is produced by renewable power generation? Well, there might be some spatial relationships within about how counties affect each other, but then a lot of these rules, a lot of the structure of power generation is done at the state level through state law. So you might have some variables that are only measured at the state level, like what kind of incentive structures do they have for renewable power in that state, but then other kinds of variables about, again, income, social capital, education levels, they might impact people's choices as to whether they want to use renewable power within those counties or not. So that's a hierarchical model, two different spatial levels, one nested within the other, the counties nested within the states. So Don Lacombe has been doing some interesting work on that for the last few years. Additionally, it's not just continuous variables that people use these spatial models with. You can do probits, lobits. There's been some work with tobit models, and there's been some work with Poisson count data variable responses as well in spatial models. So it's flexible. It's kind of hard sometimes to find the right person who has the right code to get you where you want to go with some of these other models, but there has been some research done and some papers published using these other kinds of limited dependent variable functional forms. This will be the last thing I do here in this video, because this is getting quite long now. So one other thing that I want to make sure that you are aware of is that there are groups out there who do not like spatial econometrics. There are some people who have a hatred of spatial econometrics. I have friends who have been called crazy idiots because they even mention the idea that they're going to use spatial econometrics. You need to be aware of this. You need to be aware of some of the critiques, that there are some editors at some journals and some bosses that you might run into. They're either not aware about how good spatial econometrics is, or maybe they're aware of something that some of us aren't. And you need to read some of these and be aware of some of these issues before you head down the road of learning about this. At least be aware of what some of the criticisms are. And a good place to get started, I have this link here, but let me just show you where this goes. This is an issue of the Journal of Regional Science from May 2012, where the first few articles here are all criticisms of spatial econometrics. So Mark Partridge, one of the editors of the Journal of Regional Science, is an sometimes vocal critic of spatial econometrics. Another article here called Mostly Pointless Spatial Econometrics, which you see as open access, so you don't have to pay to get it. I really think that you should take the time to download and read through this paper, Mostly Pointless Spatial Econometrics. And they bring up some criticisms, including they don't think that these models are well identified. Other criticisms that I've heard are that it's another degree of freedom that it gives you in trying to construct a model. You keep playing around with things. You know, if you torture the data long enough, nature will confess. So if you have not only functional forms to choose and variables to choose, when it comes to p-hacking, now you have all these different ways you can construct weights matrices and all these different ways that you can assume that neighbors are related to each other. And is it the value of the dependent variable? Is it the explanatory variables? Or is it the error terms? It gives you a lot more freedom to maybe find a relationship that's not really there. If you search through enough models, you'll find something, even if there's not really anything going on. So these are some of the criticisms that you will hear people go through. Let me just breeze through. I'm not going to go through everything here. Here are some books to be aware of. We're going to go through and use Geoda here in a video coming up very soon. Here's a link to Lesage and Pace's book, Introduction to Spatial Econometrics in 2009. Paul Elhorst is also a very, very good writer, very knowledgeable guy on this subject. I love Paul because what he does is best, in my opinion, is he takes a lot of the research and he can, in very clear language, summarize what's going on for you. A lot more easily digestible than reading a lot of separate papers. And he has this short book that he wrote. Here's some other papers that I mentioned before, some others that I didn't mention. A really good overview where Elhorst discusses Lesage and Pace's book and gives his opinions on the idea, and Elhorst on some dynamic spatial models. The third page here is on some software that we'll talk about, but this video is too long, so I'm not going to talk about that right now. But as I said, download this, go through it, and keep your questions and comments coming. I love the interaction with you guys. If there's anything I can do differently or do better, let me know. And as always, if you like this video, please give me a thumbs up. If you don't like it, please give me a thumbs down. And keep in touch, guys. Talk to you later.